Today I am taking lecture on modeling of environmental dispersion. This is the last lecture on the air pollution. Now first see the what is the mathematical modeling. In mathematical modeling we collected the some secondary data through the literature or some already exists database, or we do the some experiment in the field or in the lab to get the primary data. These data we can say the input data for mathematical modeling, and this is mathematical modeling is a program or mathematical formula generated based on the some past data, and these mathematical formulas are solved by the some programming technique which for which purpose we use the computer systems, and this mathematical modeling give the some result or give the some forecasting basis of the these already exist data or with the basis of the primary input of the primary data. So application of environmental dispersion models. So here we are talking about the mathematical model, but these mathematical model which are used we are using in the case of the air pollution modeling. The dispersion models are used to estimate the downwind ambient concentration of air pollutants or toxins emitted from the sources. They can also be used to predict future concentrations under specific scenarios, like the changes in emission sources. They are most useful for pollutants that are dispersed over large distances and that may react in the atmosphere. Dispersion models are important to governmental agencies tasked with protecting and managing the ambient air quality. The models are to determine whether existing or proposed new industrial facilities are or will be in compliance with the ambient air quality standard. Now input data. What input data required for to input in these dispersion models? The dispersion models vary depending on the mathematics used to develop the model, but all require the input of data that may include meteorological conditions like wind speed and directions, amount of atmospheric turbulence, ambient air temperature, the height to the bottom of any inversion aloft that may be present, cloud cover and solar radiation. This is all about the input data of the meteorological condition. Here we are talking about the aloft inversion. So aloft inversion means generally we see the near about the earth, this is hot air, and when we go up in up direction, so there is a cold air, cool air, and then cold air. But in case of aloft inversion, in near about the surface, cold air, and then inversion, and in that inversion air there is a warmer air and again the cold air. Second input data, source term, the concentration or quantity of toxin in emission and temperature of the material. Emission or release parameters such as source location and height, type of source, and exit velocity, exit temperature, and mass flow rate or release rate. Terrain elevation at the source location and at the receptor location, such as nearby homes, schools, businesses, and hospitals. The location and width of any obstructions such as buildings or other structure in the path of the emitted gaseous plume, surface roughness, or the use of a more generic parameter, this is ruler or city terrain. So this is a mathematical model. Here some model input parameters, then emission data, and here the some meteorological parameters as a input, and finally we get the air quality on the analysis of, in this mathematical model. So there are different types of air quality models are available: deterministic, statistical, and physical. Deterministic models, steady state or time dependent; statistical, regression or empirical; physical models, wind tunnel simulation. So in deterministic, in case of steady state, there is a Gaussian plume, and time dependent, in case of time dependent, there is a box, grid, spectral, puff, and trajectory. Now deterministic approach. What is a deterministic approach? In deterministic mathematical models, these models calculate the pollutants concentration from emission inventory and meteorological variables according to the solution of various equations. Dispersion is equal to transport plus dilution. What is the transport? It is also termed as advection, most obvious effect of atmosphere on the emission, implies transport of pollutants downwind of the source. What is the dilution? It is also termed as mixing. It is accomplished through turbulence. Now limitation of deterministic approach. Inadequate dispersion parameters. Gaussian based plume models perform poorly when wind speeds are less than 1 meter per second. Numerical models have common limitations arising from employing the K theory for the closure of diffusion equation. What is the K theory diffusion equation is valid only if the size of the plume or puff or pollutants is greater than the size of the dominant turbulence eddies. In Gaussian puff models, relative diffusion parameters are derived from very few field experiments, which limits its applicability. Large computational cost in terms of time and storage of data in numerical models require large amount of the input data. So these are the limitations. Gaussian plume dispersion models. Now what are the assumptions in that model? Steady state conditions, which implies that the rate of emission from the point source is constant. Homogeneous flow, which implies that the wind speed is constant both in time and with height. Pollutants is conservative and no gravity fallout. Perfect reflection of the plume at the underlying surface, means no ground absorption. The turbulent diffusion in the x direction is neglected relative to advection in the transport direction. The terrain underlying the plume is flat. Now development of this Gaussian plume dispersion model. Consider a point source somewhere in the air where a pollutant is released at a constant rate q, kilogram per second. The wind is blowing continuously in the direction x with a speed u, meter per second. The plume is spread as it moves in the x direction such that the local concentration C xyz kg divided by meter cube at any point in space form distribution which have shapes that are Gaussian or normal in planes normal to the x direction. Now this is the picture. Point C, This is shown in the case of elevation. So here we are seeing the z or sigma z, and in case of plan we are seeing here y and sigma y. In the lateral y direction, the profile shape is given by 1 divided by sigma y into root 2 pi into e power minus y square divided by 2 sigma y square. While in the vertical or z direction, it is given by 1 divided by sigma z into root 2 pi into e की power minus z square divided by 2 sigma z square. The parameters sigma y and sigma z are the standard deviations of these Gaussian distributions, which indicate the spread of the plume in the y and z direction respectively. They increase with the distance x from the source. The area under the distribution determined by integration of the function given above between plus and minus infinity, and this is equal to the unity. Combining these two dimensional shape distribution by multiplying the function together give us the function for the shape of the distribution in 3 dimensions, like 1 divided by 2 pi sigma y into sigma z into e की power minus y square divided by 2 sigma y square into e की power minus z square divided by 2 sigma z square. Now concentration is equal to rate of emission from the source divided by wind speed and multiply by the shaping function. So the concentration at any point is now given by C x y z. We are taking all these 3 values is equal to Q, this is the rate of emission, divided by U, this is the wind speed, multiply shaping function, this is the 1 divided by 2 pi sigma y sigma z into e की power minus y square divide 2 sigma y square into e की power minus z square divided by 2 sigma z square. The direction measures y and z normally from the x-axis. The x-axis may also be considered to be the direction of the central line of the plume, as we are seeing in picture. In practice, the source will usually be raised above the ground. For example, the exit of a chimney. Hence, we need to modify the z coordinate so that it is measured from the ground. So we are seeing in the picture the height of chimney is small hx, and the capital H is the effective height of the plume. So considering all these things, the equation is C xyz is equal to q upon u into 1 upon 2 pi sigma y into sigma z into e की power minus y square divided by 2 sigma y square into e की power minus in bracket z minus capital H square, h minus h का whole bracket close whole इसका square divided by 2 sigma z square. So there is one further modification to be made to this equation. Unlike a plume spreading in free air, most plumes will be emitted close to the ground, like the case of the chimney shown above. Hence, as the plume is spread downward as well as upward, as it moves downward from the source, it will eventually hit the ground. Clearly, the plume cannot continue to spread into the ground. Instead, it is reflected back into the air above the ground. The effect of the ground boundary is included in the concentration equation mathematically by using a fictitious mirror image source as I is equal to S of the same strength Qi is equal to Q, placed at the same distance from the ground HS, small hs, but on the other side of the boundary. And we are seeing this as in picture. The same explanation already I have said. Hence, at any point P, there is a contribution to the concentration Cxyz from both the real source S and the imaginary source Si. The vertical distance to P from the central line of the real plume is Z minus capital H. The vertical distance to P from the central line of the imaginary source is, in that case, Z plus capital H. The lateral distance Y into the same, the lateral distance Y in both cases is the same, because all these things we are taking in the Z direction. Now considering all these things, the Cxyz now is equal to Q upon U into 1 upon 2 pi sigma y sigma z into e की power minus y square divided by 2 sigma y square in bracket into e की power minus bracket z minus capital H का whole square divided by 2 sigma z square plus e की power in bracket minus z plus z का whole square divided by the 2 sigma z square. If only concentration at ground level are required, for example in assessing the exposure of crops or humans to the pollutants, then we can simplify the equation by setting z is equal to 0. So equation comes Cxy, and in place of z we kept the 0, is equal to Q upon U 1 upon pi sigma y into sigma z into e की power minus y square divided by 2 sigma y square into e की power minus capital H square divided by 2 sigma z square. Here z is we keep the z is equal to 0. If only concentration at ground level on the center line of the plume along the x direction are required, then the equation is simplified further, since both z is equal to 0 and y is equal to 0. In that case, Cx00 is equal to Q upon U into 1 upon pi sigma y sigma z into e की power minus h square divided by 2 sigma z square. So here Pascali stability classes are A. extremely unstable, B. moderately unstable, C. slightly unstable, D. neutral, E. slightly stable, F. moderately stable. So basis of this class, here is a graph are available, and basis of this graph we can get the value of the sigma y and sigma z. We are taking here as an example. We will solve the problem. A chimney with an effective height of 70 meter discharge sulfur dioxide at a rate of 100 gram per second, and the average wind velocity at the top of the chimney is 4 meter per second. assuming atmospheric condition to be moderately unstable. So condition is available. So basis of this condition we can get the data of the sigma y and sigma z. Find the concentration of SO2 at ground level at the distance of 0.2 km downwind along the central line of the chimney and at 0.03 km on either side of the central line at that location. So from these graph we can get the sigma y, value of sigma y and sigma z basis of these moderately and unstable conditions and at a distance of the 200 meter. Now use the equation. Now use this equation. Cx is equal to q upon pi into u into sigma y into sigma z into e की power minus 1 by 2 in bracket h square divided by the h square divided by sigma z square. So put all these value here, we get the answer 22 gram per meter cube. Now concentration of the gas at a distance of 0.03 km away from the center line is given by Cxy is equal to q divided by pi u sigma y into sigma z into e की power 1 minus 1 by 2 y upon sigma y square into e की power minus 1 by 2 h e divided by sigma z का whole square. So putting all these value here again we get the result 17 mu gram per meter cube. If the burning is assumed to be taking place at the ground level, no chimney is provided and SO2 is emitted at the ground level, the concentration of SO2 will be given by equation Cx is equal to q divided by the pi sigma y sigma z into u and get the result 9.95 milligram per meter cube. Now in these all these scenario we have to know the plume types, how many types of plume may available. Plume types are important because they help us understand under what condition there will be higher concentration of the contaminants at ground level. Looping plume, high degree of convecting turbulence, super adiabatic lapse rate accompanied by strong solar heating and light wind. High probability of high concentration sporadically at ground level close to stack occurs in unstable atmospheric condition. We are seeing the looping plume, coning plume as you are seeing the picture, is stable with small scale turbulence associated with overcast moderate to strong wind, roughly 10 degree cone. Pollutants travel fairly long distances before reaching ground level in significant amount. Occurs in neutral atmospheric condition. Fanning plume occurs under large negative lapse rate, strong inversion as a considerable distance above the stack, extremely stable atmosphere, little turbulence. If plume density is similar to air, travel downwind at approximately same elevation. Lofting plume, favorable in the sense that fewer impact at ground level. Pollutants go up into environment. They are created when atmospheric conditions are unstable above the plume and are stable below. Fumigation, most dangerous plume. Contaminants are all coming down to ground level. They are created when atmospheric conditions are stable above the plume and unstable below. This happens most often after the daylight sun has warmed the atmosphere, which turns a nighttime fanning plume into fumigation for about a half an hour. This is all about the plume. Now, thank you.